Hi everyone, my name is Wouter Emery and I'm the founder of AirShaper. Today I will introduce AirShaper to you, which is the online platform to run automated CFD simulations for external low-speed aerodynamics. And it's based on OpenFOAM, which is, as you probably know, a very powerful open source environment to run CFD simulations, but it's also quite complex and it doesn't even have a graphical user interface. And there are literally hundreds of settings that you need to set in terms of meshing, solving, post-processing, and so on to obtain reliable results. So to make aerodynamic simulations accessible to small and large companies, we've built this platform where you simply pay per simulation instead of buying a license, and everything runs in the cloud, so you don't need software or hardware, and you don't need someone with highly specific experience in terms of CFD simulations, because everything is automated through intelligent algorithms. So let me just run you through the platform. The first step is to upload your 3D model, which is something I've done here. And we accept models in STL, object, or step file format as a single file. So even if you have a car or an airplane with hundreds or even thousands of individual components, that's fine. Just export as a single object file or STL or step. We will convert it for you for easy viewing in the browser. And we accept files up to 3 gigabytes and with up to 10,000 individual components. So one additional remark is that we can also work directly with what we call non-watertight geometry, which means that there can be small gaps or holes, which normally crash a CFD simulation. But in our case, you can just work with those models. Our platform is flexible with those, which means that you don't need to spend days or even weeks to prepare or repair your CAD model for CFD simulations. So we can work with non-watertight and non-manifold 3D models. Then it comes down to setting up your simulations. So we have these very simple questions here, like is it on the ground or above the ground? If you would do a drone simulation, for example, could be above the ground. I'll show one later on. In this case, it's a car, so it's on the ground. Static means that it's a standstill object with air moving across. In this case, it's the opposite. It's an object moving through standstill air, which is the case for this vehicle, which means that visually, but also behind the scenes, we will add a moving ground to the simulation. Now, if your 3D model is not positioned correctly, so this one has the same coordinate system as our application, but if it's not the case, you can just align it properly with the driving direction. You can also add like a 5 or 10 degree side slip angle to take side winds into account, and so on. You can specify the velocity. Yeah, by the way, we also do hydrodynamic simulations for fully submerged objects. So back to the velocity, imagine this one is going 180 kilometers per hour. And you need to specify the units. STL files don't store units. They only store the vertices in just a unified coordinate system. So you need to specify the units. And once your simulation has been set up, we have this interface that will automatically detect the rotating wheels on a car. So even though this is a, well, with all due respect, but a dumb STL file, which doesn't contain intelligence like a radius or a distance or anything, we automatically detect which parts are wheels, and we will automatically find the central axis of rotation of a wheel, and we will apply a rotational velocity which matches the forward driving speed of the car via the radius of the wheels. So I just clicked one button and now I click done, and that's the only thing you need to do to set up rotating wheels. You can still modify them if a component has been added that shouldn't be added, and the other way around. What we also offer behind the scenes through porous elements is the option to add radiators. So I just clicked this radiator here and we'll automatically find this element. We'll automatically find the direction of the flow through the radiator, so you don't have to specify any coordinate system or anything. This is all automated, and the only thing we ask for are 2 points on the pressure drop curve. So 1 point, let's say 1 meters per second and 10 pascals in pressure drop. Second point on the curve, 2 meters per second and 30 pascals pressure drop. That's the only thing you need to do to set up radiators, and again, you can click done. And that's it. That's the way you set up a simulation on AirShaper. All the rest is done in an automated way. And by that, I mean literally everything. So we schedule a machine automatically to be launched on the Google Cloud, where we use high performance computing to speed up the simulations. A regular one like this one would take just 4 hours or something to be completed. You can launch as many simulations in parallel as you like. And the whole setup is automated all the way from sizing the virtual wind tunnel, which includes looking at the aspect ratio, the length, the height, the width of an object, to make sure that we have enough capturing of the wake downstream, that we have enough upstream length of the wind tunnel. We automatically size the wind tunnel so that we have a blockage factor, a blockage ratio of less than 1%. To not bias the results too much, and even then we still apply a correction for the blockage factor. We have adaptive mesh refinement, which I'll get to later on, to automatically refine the mesh after the first simulation based on the gradient of pressure and the vorticity. We will refine the wake of the car. We will refine high pressure gradient areas like the leading edge of airfoils and so on. So all of that is automated, and once a simulation has finished, you get this. So basically you get a number of things. One is that you get a PDF report, which is this one, which will show you all of the details of the setup page that you have just set up. So that's interesting, the number of cells that were used, the model of the 3D file, the name of the 3D file. We automatically calculate the frontal surface area, so you don't need to do this yourself. We make this projection, actually this view, and calculate this for you. What you see here is actually the meshed model, so it's not the original STL file, this is the meshed model. And as you can see, we capture a lot of details, even though this is just our medium accuracy simulation level. And this is because of the adaptive mesh refinement, which will refine around problematic areas in terms of flow, which are very difficult. So you see that even the individual spokes are captured nicely, the splitter, the dive planes here, even the gaps between the door and the rest of the bodywork, all of those are captured in this mesh. Then if we continue to the rest of this report, we see here a table which documents the forces in X, Y, Z, so drag force, lift force, or down force in this case, and the lateral force, if any. And we also calculate the pitch, roll, and yaw moments on the object. We provide a curve illustrating the convergence of the simulation and the length of the averaging window to obtain a reliable force and moment value for the averaged fields. We calculate the drag coefficient automatically. This is a race car, so typically it's very, very high. And then we calculate the aero balance automatically, which we can do so because we know where the wheels are, because they were detected automatically. So we can calculate the front lift coefficient and the rear lift coefficient. In this case, both feature tremendous downforce values. Then if I continue, I will close this one. This is all included in the report, renders of pressure clouds, CP clouds, and so on. I'll close it because this is all available online as well. So you don't need to install anything. This all runs in your browser because these are compressed models for easy viewing. And the first thing that we show is what we call the 3D pressure clouds, which is an illustration, or actually technically it's an isosurface of the total pressure coefficient of 0, which in 3D denotes where you have high sources of energy loss. For example, if you look at this car, the wheels are always typically a problem, but this also reveals the structure and location of vortices. So you see here at the front splitter, they have vortices curling around the inside of the wheels. You have these channels, vortex generators, diffuser setup, which is full of vortices, which is actually intentional on this car to generate downforce. What you can also see is that in some areas, you'll still have flow separation, like there's a bit too much pressure here around the side inlets, so the air needs to jump up, and this creates a semi-separated vortex here. You can see flow separation here in the areas where the air needs to dive underneath the car and then needs to follow some negative curvature here behind the fenders on the front wheels. We can see that this outlet here of the cabin, slight bit of flow separation, but not much actually. The design of this car is actually quite good. You can see Strong wingtip vortices here around the side plates of the rear wing, which is normal, but still very interesting to see. This would be a good indication as to where you can actually resize or reshape these end plates. And obviously the entire wake behind the car, the air which is being kicked up by the diffuser. This is causing tremendous downforce, but also quite a bit of drag. We also show the surface pressure. So obviously you'll see high pressure on the top of the airfoil elements. So they're pushing the car down. The front wing, it's not just a splitter, it's really a wing element in this case. And then at the bottom of these elements, you'll see the opposite, which is a very low pressure, especially because this one is in ground effect. And you'll see the effect of the diffuser pulling air underneath the car, accelerating it, and creating low pressure here at the center of the car, which is good to maintain a proper aero balance. Then we also show the surface friction. So in essence, the friction itself is a bad thing, but usually the pressure drag is dominant. So the friction map is typically a very good tool to analyze wherever it's low to spot areas of separated flow, which you can see here, very typically behind the top part of the front wheel, because this one is moving forward at twice the vehicle velocity at the tip of the tire, which means you get a lot of turbulence, and this area is full of disturbed flow. You can also see stagnation areas at the front of the car, and if you look at the bottom of the car, you see nice speed up and surface friction at the bottom, and you'll see flow separation at the rear, obviously, because the air can never follow a curvature which is almost perpendicular to the flow. That's quite normal. And the surface streamlines, which are these black lines, they indicate how the air flows across the surface. So you can see that it nicely follows this shape of the cockpit here. You can see the way that it slightly curls outward here on the wing to tip over and form that wingtip vortex and so on. Then we have an illustration of the flow lines. So the vertical streamlines, we've made them dynamic, so you can actually drag them left to right, so that you can analyze the flow as it moves across the car. You can do the same for the horizontal streamlines, which is quite interesting if you position them just below or above the rear wing, for example. You can go to zoom in, see how the air gets accelerated and gets kicked up massively behind the rear wing to generate that downforce with the two-element wing. We have a rough indication of wind noise. This is not an acoustic simulation. That would be way too expensive to offer in our existing pricing model. But this is a translation based on a acoustic analogy to translate turbulent kinetic energy into noise energy, just to spot the biggest sources and areas of wind noise. Then, as mentioned, we automatically split your model into separate components, which means that you can afterwards click on those components, just as easy as this in your viewer, and then analyze the forces for each individual component there. What we also have is what we call elements, where you can, sorry, I clicked the wrong one here. This is the flow through the radiator. So as you can see here, there's a flow inlet, which is over here, and then it dives down and then is forced through this radiator. So most of the flow goes to the end of this channel where it gets blocked in the wedge between the radiator and the channel, and then is forced through, which is why most of the airflow is actually going through the lower part of these radiators. You can also look at the pressure field, and there you see a similar story. So high pressure at the lower part, low pressure here at the top. So that's in a nutshell what we offer: the PDF report, the online visualization, and for those who want to dig in and do their own post-processing in ParaView, you can. We provide the full simulation data in OpenFOAM format, so you can actually do your own analysis later on. So that was it for a 3D model of a race car. I've also taken one of a drone. This is again a public model. You can also check the public results. So be sure to make a free account at airshaper.com and just log in to your dashboard and then go to sample projects, and then you'll find these projects and many others. So this is a student air race prototype where they asked us to run an analysis, not just to look at the performance of the drone, but also to look at the cooling of components inside. So even though we don't include thermal effects, looking at the local relative velocity around certain components or heat sinks can be quite interesting. And in this case, they are located on the inside here, just below the nose. We have some cooling components. You can see the fins there of the cooler that they want to optimize. So in this case, what we do is that we say that this one is, let's going at 70 kilometers per hour forward. You need to provide an estimate of the forward angle of attack of your drone. Let's say that in total it's 50 degrees. Let's specify the units, which would be millimeters in this case. And then we have this interface where you can automatically set up a propeller. So the only thing we ask you to do is to click the propeller or all the components of a propeller and click OK. And then our software will automatically find, again, the central axis of rotation, and you can set the RPM and so on. You can do this for other propellers, which are just below here. So I can do a second propeller. It'll automatically copy the RPM that you set for the first propeller. Now this one, oh, my apologies, needs to rotate in the opposite direction. There's a mistake here. That was my bad. So this is the way you can set up propellers and actually set up your entire simulation. If you then go to the results again, which I can show here. So what you can see, again, we have the full PDF report. I will not repeat myself, but same things, pressure clouds. So you can see the massive wake which is being generated by this bodywork, which is nice and streamlined up until this point where this edge is creating flow separation. You can see that the landing gear is causing flow separation as well, lots of drag. And then the propellers themselves, even though the goal is to analyze the effect on the main drone and not necessarily to predict the thrust and the torque accurately, we still do come up with a fairly interesting prediction of the values there. So if I go to rotating objects, we can actually click on a propeller, and then you'll see the streamlines through that propeller. You can see the power, which is 50 watts in this case. You can see the torque, the RPM that was set, and the thrust. And actually they match pretty well in this case with what the students had calculated and used as input or design values. And what's also interesting to see, because these are counter-rotating propellers, is that the first propeller adds this swirl to the flow, which is normal, and the second one counteracts this swirl and provides more or less streamlined outflow of the air behind the combined setup of these propellers. So that was just an example of how to set up a propeller simulation on a drone. There are plenty of sample projects, be sure to check them out. I'll go to the next thing. So if you go to airshaper.com, if you're just looking for information, we have a huge database by now, of interesting topics on aerodynamics. We have practical applications, like for example our Formula 1 challenge, where the community has contributed to the redesign of a Formula 1 model that we created with a company called Voyager. Super interesting. We really increased the downforce, reduced the drag over multiple iterations, and we're now doing the same for MotoGP. So if you want to join, just check it out, go to our website, and join the craze. We use our platform to design a 300 mile per hour, at least that's the goal, hypercar. It has been tested already with the Aero package that was designed completely with AirShaper. It already hit 447.8 kilometers per hour. We analyzed 3D scans of cars like the Rivian, and the pretty cool thing is that Rivian actually came in and said, yep, what you said is actually correct. We have some more fun topics. If I just browse through this quickly, we have interviews with NASA, where we discuss their electric aviation concept. We interview solar cars, Formula 1 in schools. We have a program with free credits for students. Like I mentioned, the 14-year-olds using our platform, this is mainly it. Instruction videos on how to set up propellers and so on. Interviews with one of our customers, electric motorbike manufacturers. If I just continue, we have theoretical explanations on what is flow separation, what are boundary layers. We go for test drives in real cars to analyze their aerodynamics, explain their aero features. We also have adjoint shape optimization, which is a tool where our software will automatically optimize the shape of a vehicle, something that we've also done for customers like Aptera in the United States. If I continue, there's theoretical explanations on how wind tunnels work, why golf balls have dimples, and why it's usually not a good idea to add it to your design unless it's a very specific setup. How to process your results in ParaView. We have a free instruction video on how to do that. Interviews with Ocean on their new SUV. MotoGP interviews with one of our customers, MV Agusta, interviews with designers like Louis Vermeers, who is a famous designer, designed the Ferrari 458 and so on, interviews with Airbus. And if you continue, I think we've almost reached the end of our database. Yeah, Tesla, semi-analysis, glider plane basics. And I think that's about it. Yeah, vortex generators, this might be interesting. If you want to experiment yourself with vortex generators, this could be cool. Another thing that we do is post blogs. So we interview companies like sports clothing companies, how wind tunnels work, how EASA, the European regulator, is actually integrating CFD more and more into the design process. So there's plenty of things that you can find here for more details. And then to validate our tool, obviously, because people do need to believe and trust in AirShaper, we have a number of validation cases done by third parties, not by ourselves. So, for example, this one, Wingtra, is a Swiss drone manufacturer. They took their latest design, not this one, because the new one is confidential, to the wind tunnel. And these are the correlation curves. So AirShaper in orange and wind tunnel in blue, which is the correlation between wind tunnel drag force and simulated drag force. And the same for the lift. As you can see, we have very good correlation. In some cases, just when there's separation, which is typically a tricky point, not just in CFD, but also in the wind tunnel, because if you prototype, the roughness of your surface might differ from what you do in the virtual world. Nevertheless, very good correlation here. The same for a Cessna airplane. This was done by NASA long time ago, and then Dark Corporation, an independent company in the States, compared our simulation results to Flightstream, which is software that they use, Star CCM, so very good correlation, and then to the wind tunnel data, which is also good correlation here. And again, at low angles of attack, all simulation softwares differ from the wind tunnel test, which is probably explained by the fact that in the 3D model there are no vortex generators or small gaps, which might have been present in the real model plane. Then we have AVL Racing, who took our platform for a spin and applied it to their race car. We have a very, very good correlation in terms of quantitative and qualitative comparisons between both platforms, as you can see here. And then the 3D scan of a Tesla that we got was compared to a physical car that was taken to the wind tunnel in the S2A wind tunnel in France. And we had less than 6% deviation between wind tunnel simulation and our CFD simulation, also wind tunnel test and CFD simulation. And also in terms of qualitative flow results, this is a slice taken 100 millimeters behind the car, both in the wind tunnel and in simulation. And again, you can see very good correlation of the vortex structures and so on. So if I close this one, maybe to zoom in on our adaptive mesh refinement, which is something that I will explain on Friday during this OpenFOAM workshop, in a session where we explain adaptive mesh refinement and convergence detection. So we've made some of this open source, so you can download this, implement this yourself, and start playing with adaptive mesh refinement, which exists in OpenFOAM for the volume mesh, but not for the surface mesh. And this is what we've implemented. So you can refine the mesh based on flow fields, which you can choose yourself or use the ones we have defined, and then refine the mesh step by step. So if you go back to the top of the page, maybe one last thing to show is the optimization. So as mentioned, we have a module to perform adjoint shape optimization simulations, which is an option where you design or create a design space, in this case the wingtip of a Cessna, and then we ask the software to optimize towards a certain goal, which in this case was to generate more lift. And as you can see, as we move this slider, this simulation optimized the wingtip into a very organic and nice looking shape, actually, without us telling it to do so. So the only thing we asked for was more lift, and with a more or less constant drag, we increased, or the software increased the the lift coefficient by more than 50%. Of course, for one angle of attack, needs to be checked for other angles of attack, but this is a very, very powerful technique. So that's it in a nutshell what we do at AirShaper. If you have questions, just let us know. And if you just want to try the platform, it's actually very accessible. A single one-off simulation at regular, which is 10 million cells, will cost you just 500 euros for a single simulation. If you really want to perform a lot of design work, you can go for a subscription, which is a 10,000 euro package, valid for 12 months. And you can use the credits both for simulations, whether it's a basic, a regular, or advanced, so 1, 10, or up to 100 million cells, or consultancy. That means with the same bundle, you get access to simulations, but also to our aerodynamics expertise to assist you on your design, to help you understand flow results, to help you redesign, or give you at least the input on how to redesign your geometry to improve aerodynamic performance. So it's a one bundle solution for both simulations and aerodynamic support, so you can really bank on that to cover your aerodynamic needs. That's a bit in a nutshell what we do. If you have questions, just drop me an email at info@airshaper.com. That will end up in my personal mailbox. And yeah, let's just set up a call. Thanks a lot. If you have any questions, yeah, just let us know. If you have any comments, drop them on the platform or wherever you see this, and talk soon. Thanks. Bye-bye.